depends on the fuel itself. You're going to actually experience it in your class where I'm going to have to do a lot of problems where you actually try different fuels. If you started doing the homework, actually, you have to do this as well. I give you different fuels. But let me just touch base in the last 5 minutes, the lean condition and the rich condition. So what if I have excess fuel or I have excess oxygen? What happens? So if the fuel air to ratio that I compute is less than F stoic, which are stoichiometric condition, then what do I have? I have excess what? And if it's greater than? If F is less than F stoic, what do I have? Excess air. Meaning what? Meaning lean fuel. That means I have too much air relative to how much fuel I'm dumping into my system and burning. And this obviously excess fuel. Now I'm being on the non-efficient side of things. So this is rich fuel. Okay, so let's outline the equation for it. And what we characterize it is, we say, how do I keep doing this? I would say equivalence ratio. This is what we're talking about. Which characterizes the ratio of this relative to this. So essentially, it's phi is equal to F, the one I computed, relative to my ideal condition that I burnt everything. So F stoic. And if I am at stoichiometric condition, what is phi equal to? 1. So that's stoichiometric. So this is very critical. If you want to work in propulsion field, you need to know that information. So what if I have phi less than 1? Phi less than 1 means that I have what? Lean or rich? OB? Lean. So lean means excess air. So what does that mean? Or how do I compute this? What I get is CH4 plus 11, this is an example, N2 0.21 of oxygen will give me H2O plus CO2 plus E of nitrogen plus O2. I have a little bit of excess oxygen. So from this, I can compute my amount of nitrogen, or if I have a rich condition, rich, excess fuel. Let's say I put too much molecules of my composition of fuel, so 1.3 CH4, and keep the air at the same level, 9.52, 0.79 nitrogen plus 0.21 oxygen. And what am I going to get? I'm going to get H2O.
No, it cut out.
H2O plus CO2 plus 7.52 nitrogen. And what am I going to get? I'm going to get A of multiplied by, I'm going to write it right here, A multiplied by CH4. From that, you could compute, you could do the balance like we just did earlier, and what are you going to get for these compositions? For E, I got it for you, or A at least, A is equal to 0.3, and from that, what you're going to get is the fuel to air ratio is 16 kilograms over 211.1 kilograms, and that is going to equal to 0.076. Now notice it's on the higher end, but it's what? It's fuel for this problem. Fuel rich. It's not stoichiometric. Right? This is higher than this. Because I put too much fuel. I put too many molecules of fuel. 130% of what I'm supposed to put generally to get the stoichiometric condition. So that's why it's rich. So essentially that's what it is, just ratios in general. Now, just a FYI, your car engines, why are we getting more miles per gallon than we did a year, so 10 years ago? Cars 10 years ago were around 20 miles per gallon. Now you try to buy a car and it's within 30 to 40 miles per gallon. What are we doing differently? More air, essentially. You're running in car combustion chambers, they're most likely running rich back in the day by design. So now they're actually trying to optimize it to get closer to a stoichiometric condition. We're still not in a stoichiometric condition. Your car engines are running rich, you're actually passing fuel through there. If you do get the stoichiometric condition, you will be well over 100 miles per gallon. So, same thing applies for propulsion systems as well. We'll talk about it
Right now.